For almost 40 years, scientists thought they understood Uranus. But what if the only time we ever visited it, we caught it on the worst day possible? When Voyager 2 flew past Uranus in 1986, it didn't just see a cold, quiet planet. It recorded violent radiation, chaotic magnetic forces, and energy levels that made no sense. Uranus looked extreme, almost broken. And for decades, no one could explain why. Here's the crazy part. Voyager 2 wasn't wrong. The science wasn't wrong. The timing was. New research reveals Uranus wasn't acting normal at all. It was in the middle of a rare, explosive space storm, a cosmic event so perfectly timed that it fooled scientists for generations.
If you enjoy deep dive science documentaries like this, focused on real data, real mysteries, and the edges of human knowledge, consider subscribing. New videos explore the universe where certainty ends and discovery begins. And let us know in the comments what you think. Thanks for watching.
And once you understand what Voyager 2 actually flew into, you realize this wasn't just a discovery about Uranus. It changes how we understand an entire planet and why we urgently need to go back. For decades, Uranus carried a strange reputation among scientists. It wasn't just distant or cold, it was confusing. Everything Voyager 2 recorded during its 1986 flyby suggested Uranus was an extreme, chaotic planet. Its radiation levels were unexpectedly high, its magnetic environment looked violent and unstable, and its space surroundings didn't behave the way scientists thought they should. The problem was simple. There was no second visit to compare it with, so for nearly 4 decades, what Voyager 2 saw became the default truth about Uranus. Even though it may have only capped, Voyager 2 is one of the most successful spacecraft ever launched. Sent into space in 1977, it was designed to take advantage of a rare planetary alignment that allowed it to visit multiple outer planets in a single journey. By the time it reached Uranus in January 1986, Voyager 2 had already passed Jupiter and Saturn. It was carrying instruments that could measure magnetic fields, charged particles, radiation levels, and plasma, the invisible environment surrounding planets. But there was one major limitation. Voyager 2 didn't orbit Uranus. It flew past it once. That flyby lasted only a short window of time, essentially a cosmic snapshot. Everything scientists knew about Uranus's space environment would come from that single moment. And that moment turned out to be very misleading. Before Voyager 2 arrived, scientists had reasonable expectations. Uranus is far from the Sun, nearly 3 billion kilometers away. At that distance, the solar wind is weaker than near Earth. Less solar energy usually means calmer space environments. Based on models and comparisons with other planets, scientists expected a relatively mild radiation environment, a stable, though unusual magnetic field, lower particle energy compared to Jupiter or Saturn. Uranus was expected to be strange, but not extreme. What Voyager 2 found instead forced scientists to completely rethink those assumptions. When Voyager 2 began sending back data, scientists were stunned. The spacecraft detected intense radiation belts, highly energized electrons, strong and erratic magnetic activity. Some of the particle energies were comparable to what's seen around much larger and more active planets. This was surprising because Uranus is not massive like Jupiter, nor does it have the same internal energy output. Yet its space environment appeared far more aggressive than expected. At the time, scientists had no reason to doubt the data. The instruments were working correctly, the measurements were consistent. So the conclusion was simple. This must be how Uranus normally behaves. That assumption would shape Uranus science for decades. Even without the radiation mystery, Uranus was already strange.
Unlike Earth, whose magnetic field is closely aligned with its rotation axis, Uranus's magnetic field is tilted by about 59 degrees, offset from the planet's center, rotating in a lopsided, wobbling motion. This creates a magnetosphere that constantly twists and reconfigures itself as Uranus spins. Voyager 2 showed that this strange magnetic geometry could trap particles in unexpected ways, creating unusual radiation patterns. So when scientists saw extreme radiation, they connected the dots. Uranus is weird, so this must just be another example of that weirdness. What they didn't realize was that something else was happening at the same time. To understand the mistake, we need to talk about space weather. The sun doesn't emit energy evenly. It constantly releases streams of charged particles, protons and electrons, known as the solar wind. Sometimes this solar wind is calm, sometimes it's fast, and sometimes different streams collide. These collisions create massive structures in space where particles are compressed, energized, and accelerated. One of the most important of these structures is called a co-rotating interaction region, or CIR. CIRs are like shockwaves traveling through the solar system. When they pass a planet, they can compress its magnetosphere, inject large numbers of energetic particles, and temporarily supercharge radiation belts. Near Earth, similar events cause geomagnetic storms and intense auroras. But in 1986, scientists didn't know whether one of these storms was passing Uranus. The biggest reason this misunderstanding lasted so long is simple. There was no way to check. In 1986, there were very few spacecraft in the outer solar system, no continuous monitoring of solar wind near Uranus, no long-term data before or after the flyby. Voyager 2 arrived, measured extreme conditions, and left. There was no follow-up. Without broader solar wind data, scientists had no evidence that Uranus was experiencing a temporary event rather than a permanent state. So textbooks, models, and mission concepts all assumed Uranus naturally has a highly energized radiation environment. That assumption quietly shaped everything that came after. Fast forward nearly 4 decades. Today, scientists have better solar wind models, decades of heliospheric data, and improved simulations of space weather behavior. Using these tools, researchers began reconstructing what the sun was doing in early 1986. What they found changed everything. Their models showed that a powerful solar wind disturbance was moving through the outer solar system at the exact time Voyager 2 reached Uranus. In other words, Voyager 2 didn't arrive on a normal day. It arrived during a rare space storm. This realization explains the mystery perfectly. As the solar wind disturbance passed Uranus, the planet's magnetosphere was compressed. Extra particles were injected into trapped regions. Radiation levels spiked far beyond normal. Uranus wasn't permanently extreme, it was temporarily energized. Voyager 2 saw Uranus at its most chaotic, not its average state. This is why the data looked so strange and difficult to reconcile for so long. It's important to be clear, Voyager 2 didn't make a mistake. The instruments worked exactly as designed. The measurements were real. The misunderstanding came from interpretation, not data.
Scientists assumed one flyby represented normal conditions. Extreme readings reflected permanent behavior. But space environments change, sometimes dramatically, depending on solar activity. Voyager 2 simply captured Uranus during a moment of rare intensity. This new explanation forces scientists to rethink many assumptions. If Uranus is usually calmer, its radiation environment may be safer for future spacecraft. Its magnetosphere may behave differently over long periods. Its moons may experience less constant radiation than once believed. It also means decades of models may need revision. Uranus may not be the wildly hostile planet it was once thought to be, at least not all the time. This story highlights a major challenge in planetary science. Many distant worlds have been visited only once. When we rely on single snapshots, temporary events can be mistaken for permanent features. Rare storms can define decades of understanding. Entire planets can be mischaracterized. Uranus is a perfect example of why long-term observation matters. This discovery has strengthened calls for a dedicated Uranus mission. An orbiter could monitor the planet over many years, observe multiple space weather conditions, reveal what Uranus is like on calm days and stormy ones. Only then can scientists truly separate what is normal, what is rare, and what Voyager 2 just happened to witness. The Uranus mystery isn't just about one planet. It's a reminder that space is dynamic. Timing matters, and first impressions can be misleading. For nearly 40 years, scientists believed Uranus was extreme by nature. Now we know something humbling. We may have judged an entire planet based on its worst day. Voyager 2 gave us an incredible gift, our first and only close look at Uranus. But it also taught us a quiet lesson. The universe doesn't always show itself honestly in a single moment. If this made you rethink Uranus even a little, drop a like. It tells us we're on the right track. And if you enjoy uncovering the stories science took 40 years to understand, subscribe so you don't miss what's next. Your support helps us keep bringing these deep dive stories to life.